Okay, it's good morning. I'm just going to do a summary of climate and weather. The first thing that I'm going to do, I'm just going to look at global air circulation. I think you can see the main topic here is climate and weather. There are certain things that you need to understand before we start with the mid-latitudes, before we also look at the subtropical anticyclones. Same applies with tropical cyclones. The first thing that you need to understand, boys and girls, is you need to understand global air circulation because it is the foundation of our topic of climate and weather. What do I mean by that? This is a model of our globe. That's why when we talk about global air circulation, this is what we are referred to as the global air circulation. So you need to identify your pressure belts. Know where all your pressure belts are. I've already drawn it on the board, as you can see. Just forgive me for my board is very small. So where we have got our equator, as you can see here, it's written equatorial low. It's an area of low pressure. That is a low pressure belt. It is also known as the doldrum. It is also known as the intertropical convergence zone. This is our equatorial low. It's a low pressure belt. It's a low pressure belt. Low pressure, low pressure belt. So that's a low pressure belt. And also as we move upwards, now latitude 30 degrees north and south, we have got what we call the subtropical high pressure belt. Subtropical high pressure belt. This you find it on both north and south of the equator. Then as you move also with your latitude, north and south of the equator, you've got the subpolar low and also subpolar low at the bottom. That is both 60 degrees north and 60 degrees south of the equator. That's where we have got the subpolar low. It's also an area of low pressure. Then lastly, we have got at 90 degrees north and 90 degrees south. This is an area of high pressure. That is a high pressure belt. We call it polar high. We call it polar high. So in summary, we have got the low pressure belt. That is our equatorial low or intertropical convergence zone. It is also known as the doldrum. That's where we've got a low pressure belt. Then from there, moving upwards and also downwards, we've got the subtropical high pressure belt. We have the subtropical high pressure belt north and south of the equator. Then we've got the subpolar low. It's a subpolar low as well, north and south of the equator, which is our low pressure belt. And lastly, we've got our high pressure belt, that is your polar high, and your polar high have got 90 degrees north and south of the equator. Boys and girls, this is very important because in order for you to understand the mid-latitudes, and also in order for you to understand the tropical cyclones, and also in order for you to understand the subtropical anticyclones, the subtropical anticyclones, you need to have a better foundation from this global air circulation. So what is it that happens when we talk about global air circulation? I think from your grade 11, I'm just going to talk about the high and the low pressure so that at least you have an idea. Low pressure, I'm just going to demonstrate. My board unfortunately is very small. Low pressure, as you can see here, I'm going to write an L to show that is low pressure. I will have two. Let me have two of these so that at least I demonstrate it fairly. This is low pressure. This is the northern hemisphere. This is in the southern hemisphere. I'm going to demonstrate first in the southern hemisphere. The direction in which the wind moves, it moves in a clockwise direction in your southern hemisphere, and in your northern hemisphere it moves in an anti-clockwise direction. Okay, your low pressure usually is associated with warm air. So warm air, when it rises, it creates a low pressure on the surface. That's why we end up having this low pressure. I'm going to sum up, assuming that we have covered this and you already know what it's all about. So in the southern hemisphere it moves in a clockwise direction. That is your low pressure. The cyclone, it moves in a clockwise direction. In the northern hemisphere, it moves in an anti-clockwise direction. As you can see, it moving in an anti-clockwise direction, which means when we are now looking at the pressure on our cell of low pressure, I would say this one, let's say, is 900. This one, I would take it as 904, which means the pressure is low in the middle. But as you move outwards, the pressure increases. That's what shows that it's a low pressure. So it moves from low to high. We've got 900 is recorded in hectopascals or in millibars, 900. Then the isobaric interval, which is the difference in terms of isobars, we've got 900, 904. Yes, 4 hectopascals or 4 MB millibars. That is the isobar interval. So this is your low pressure. We've got low pressure at the center, then the pressure increases as you go outwards. That's what resembles a low pressure. This is in the southern hemisphere, as I have indicated here, SH. So that's your low pressure in the northern hemisphere. That's also the same thing. I'll say here is 900, and outwards there is 904, which means this isobaric interval is the same. That is the 4 millibars or 4 hectopascals between the two isobars that cause areas of equal pressure. So this is your low pressure. Usually it's associated with warm air, okay? Why is it associated with warm air? Warm air is very light. As it rises, it creates that area of low pressure. That's how you end up having the low pressure. So warm air, by its nature, it's light, it rises. When it rises, what happens? It cools. And when it cools, what happens? Reaches the condensation level, clouds form, then we've got clouds of vertical extent. Usually we're talking about the cumulonimbus clouds or the nimbostratus clouds that are rain bearing. That's what the weather condition that is associated with the cyclones or the low pressure. So when it comes now to high pressure, what is it that happens? Okay, I'll say high pressure. I'm going to put my H here. I'm going to put my H here as well. This is your southern hemisphere. This is your northern hemisphere. So I'm going to compare them, both low and high pressure. This is just to jog your memory, to give you the foundation. Okay, this is your high pressure. What happens? It means now in the middle, the pressure is high. Let's say here is 900. We just subtract 4, it becomes what? 896 MB, which means the pressure is high in the middle, then it decreases as you move outwards. So that shows now it's a high pressure or an anticyclone. That's what is also known as. So in the southern hemisphere, it moves in an anti-clockwise. Okay, anti-clockwise. That is your high pressure in the southern hemisphere. And in the northern hemisphere, what happens? It moves in a what? In a clockwise. So you need to be aware that when it comes to areas of low pressure, which is your cyclone, and areas of high pressure, which is your anticyclone, okay, what is it that happens in terms of wind movement of wind? Okay, in the southern hemisphere, here it moves in a clockwise. That is your low pressure belt. That is your low pressure or your cyclone in the southern hemisphere, and in the northern hemisphere, it moves in an anti-clockwise. So once you are aware of the movement of the wind within a low pressure belt and also your high pressure belt, then you are quick to go. It will be easier for me to explain how the global circulation takes place. So this is your high pressure in the southern hemisphere. It moves in an anti-clockwise. There is high pressure in the middle, and as you move outwards, the pressure decreases. Same applies in the northern hemisphere. There is high pressure in the middle. I'm just going to do it like this. Unfortunately, my body is very small. 896, which means there is a isobaric interval of 4 millibars or hectopascals. That is the isobaric interval, which is the difference in terms of isobaric pressure between two isobars. Okay, so here in the southern hemisphere, this is your anticyclone or high pressure. It moves in a anti-clockwise in the southern hemisphere and clockwise in the northern hemisphere. That is the major difference between the two. And also your high pressure is associated with cold air. Cold air, by its nature, it's heavy. So it's heavy or it's more denser, and what happens? It subsides. It subsides, or it sinks. It subsides or it sinks, results in little or no cloud. Okay, why? Because it's cold, and cold air by its nature, you know, it does not hold a lot of water vapor. So that in itself, even when it gets to condensation, it does not release a lot of moisture. And also, if you look at the type of clouds that can form, it's just those clouds that are not bearing, like cumulus, maybe cirrus cloud, something like that. So when it comes to your low pressure, warm air, it cools. When it cools, condenses, reaches the condensation level, formation of clouds, then we have got our rainfall. Normally, the type of clouds that we have is the cumulonimbus, the nimbostratus clouds. These are clouds of vertical extent that results in storms or heavy rainfall. So that is the major difference between the two. I'll take you now to the global air circulation. Just rub off here so that it's not clumsy. Okay. So the first thing, now when you're looking now at our diagram, it shows the global air circulation. We have got the equatorial low. What happens within the equatorial low? Like I've indicated already, the low pressure, there is warm air. Remember our intertropical convergence zone, our equatorial high, the temperatures are very high within the equator. So what happens? Warm air is forced to rise. Within the equator, warm air is forced to rise. Within the equatorial, warm air is forced to what? To rise. Okay. So what happens? Warm air, since it is a low pressure, our pressure, okay, our wind, it moves from high to low. That's how it moves. So this is our low pressure here is forced to rise. As it rises, okay, goes to the upper atmosphere. I'm talking about before it reaches the tropopause, okay? Before it reaches the tropopause, so about, let's say 13, 14, 15 kilometers in the upper atmosphere. So on the Earth's surface, what happens is it converges. As you can see, it's moving from subtropical going towards the equatorial. So here it converges, and as it converges, forced to rise because it's warm, okay? As it goes up, it reaches in the upper atmosphere before it reaches the tropopause. What happens? It diverges. So here, what happens is it converges. I'm just going to use C to show that it converges. The air is moving towards each other, coming from a higher pressure, that is our subtropical high, and moving towards the equatorial low, which is low pressure. So it converges here. Since it is warm, it's forced to rise. As it rises, it cools, condensation is reached, release of latent heat, of course, formation of clouds. Then when it reaches in the upper atmosphere now, what happens? It diverges. I'm going to put a D here, which means it's moving away from each other. And when it reaches the 30 degrees north and south, it's now cold and it has got most of its moisture. What happens? It sinks. When it sinks, it creates an area of high pressure now, which is our high pressure belt, that is your subtropical high. And from there, since it's high pressure, it now moves back towards the equator. Same applies here, it moves back towards the equator. So this is your warm air, but its nature, like I've already explained, it moves from high to low. It's forced to rise. When it rises, it condenses, reaches the tropopause, 18 to 15 kilometers up in the upper atmosphere. It diverges. It's moving away from this. It's diverging from this just because now it has lost most of its moisture. It's been cooled down now. It diverges. When it reaches 30 degrees north of the equator, it's now cold. It has lost most of its moisture. Now it descends or it sinks. That's why you see these arrows that shows now it sinks. Now it's converging again in the lower atmosphere, coming back towards the equatorial low, which is an area of low pressure. So same applies here. Remember, this is a subtropical high that has been created as the air has lost most of its moisture, creating high pressure. Okay, so from here, what happens is also it moves towards the subpolar low, which is the low pressure belt. It moves towards the subpolar low, which is the low pressure belt. Okay, it moves there towards the subpolar, and when it gets there, remember this is a low pressure. What happens? It's forced to rise again. It's forced to rise again, and when it reaches the upper atmosphere, what happens? It diverges. The other one is moving towards the subpolar. Okay, it diverges. Okay, in the upper. This is in the upper atmosphere now. It diverges, which means it moves towards that direction. Yet also moves towards this direction. Okay, so when it gets there, the subpolar is now cold. It has lost moisture. It sinks. Then it moves back again towards the what? It moves back again towards the subpolar, which is low pressure. Same applies on this side. What happens? Goes up. Then what happens? Moves towards there. Here it goes towards the polar, which is high. It sinks. Then here it moving back. Okay. So you can see now in the subpolar, what is happening in the subpolar now is here in the subpolar is moving from high to low pressure, which means here there is convergence that is taking place in the lower atmosphere on the Earth's surface. Then in the upper atmosphere, what is happening? Here is moving. Okay, when it reaches the upper atmosphere, before it reaches the tropopause, what happens? It moves towards the equatorial high, the polar high here. Same applies here. It moves also towards the subpolar high, which means here there is divergence in the upper atmosphere. There is convergence, which is they are moving towards each other in the subpolar because here is a low pressure. But as it rises, reaches the upper atmosphere before it reaches the tropopause, that is from 13 to 15 kilometers, what happens? It diverges, which means it's moving towards this direction. In the upper atmosphere, it diverges. There in the lower atmosphere, it converges. Same applies when you are looking here at our subtropical high. It's an area of high pressure. What happens is going to move towards the low pressure, going to move towards the low pressure, which means in the subtropical, what happens? There is divergence on the surface, then there is convergence in the upper atmosphere. Then here there is convergence in the lower, on the surface, then there is divergence in the upper atmosphere. So understanding of the global air circulation, it helps you to have a better understanding of what we are going to look at now, which is your mid-latitudes and your tropical cyclones. You have now understand the movement of wind on a high pressure cell and also on a low pressure cell. Like I've already highlighted in the southern hemisphere moves in a clockwise. If it's a low pressure cell in a clockwise, okay, warm air is forced to rise. As it rises, it cools. Clouds are formed. When it reaches the condensation level, then we have got clouds of vertical extent like cumulonimbus. Then we have got rainfall. That is within the equatorial low. Mostly where there's high pressure, there are higher temperatures. And you can also see that within the equatorial, what is there? There are warm oceans, which means there's a lot of water vapor that is laden with moisture. And as that water vapor, that air is forced to rise, it actually results in the formation of clouds. Hence, we have got more rainfall. We have got, as the air is forced to rise, we are likely to have more rainfall. Why? Because the air that is rising is warm and it has got a lot of moisture. But when you look at this now, you are saying that when it descends now, when it has risen from the equatorial low, now it's descending on the subtropical high. It has lost most of its moisture. That's why it is now bringing about clear skies, where we have got the high pressure belt, that is your subtropical high, in the north or south of the equator, because it has lost most of its moisture. But whatever, when now it goes, okay, it goes towards now the subpolar low, which is low pressure, when it meets with the air that is blowing also from the polar high. These two air masses, that is the one that is blowing from the polar high towards the subpolar low, the one that is blowing from the subtropical high towards the subpolar low, they've got different characteristics in terms of the temperatures, in terms of the rainfall or the moisture that they hold. Hence, they do not meet when they come or when they come towards or they blow towards the subpolar low. They do not meet. Why? Because they've got different characteristics in terms of their air masses. The other one is coming from subtropical, it's a little bit warmer. This one is coming from the subpolar, it's a little bit cold. Hence, they cannot meet. They are separated by a polar front. A polar front, okay? They are separated by a polar front which is found in the subpolar low. They do not mix. Why? Because they've got different characteristics, okay? So in understanding of this from global air circulation, it makes it easier for you to understand the mid-latitudes, the tropical cyclones and subtropical anticyclones. What do I mean by that? Okay, so when you're looking at your diagram, I want to show you where we usually find our tropical cyclones and also where we usually find our mid-latitude cyclones. Okay, so before I get into that, I want also to show you something that can be assessed. I think on the first part of your multiple choice and match questions, you can be asked questions that is to do with the easterlies and the westerlies, and also with the easterlies and the osterlies, and also the direction in which they move. So from 0 to 30 degrees north and south of the equator, we have got what we call the easterlies. As you can see, I've already labeled them. We have got the easterlies. Why are they called the easterlies? It's because of the direction from which they are blowing from. You can see they are blowing from here and going this direction. That's why they are called easterlies. And if you are asked to be specific in the, on the direction in which they blow, it's very easy as well. You can see the easterlies, they blow from northeast to southwest. Where am I getting that? I'll just show you on my cardinal points. This is your, okay, northeast, south, this is your west. I'm going to do each cardinal point. This is your northeast, this is your southeast, this is your southwest, this is your northwest. In order for you not to forget this, remember your east is always on your right and your west is always on your left. So if I'm facing this direction, obviously north, this is my left, west, this is my right, east. So remember, west is always on your left and east is always on your right. So we are now saying that if you look at the direction in which the easterlies are blowing now, you can see now they are going towards the equator. Yeah, moving towards the equator, which means from here towards there, blowing from northeast to southwest. This is where I'm getting it from. Because they can ask you the direction in which the easterlies blow. They blow from northeast to southwest in the northern hemisphere, and in the southern hemisphere they blow from southeast to northwest, not north, to northwest. Okay, you can see this is the easterlies. Okay, they blow from southeast to northwest in the southern hemisphere, and in the northern hemisphere from northeast to towards southwest. When it also comes to your westerlies obviously you find them between 30 degrees north and south, 30 degrees north and south. Where do they blow from? From southwest. Now blowing from southwest to northeast. You can see in the subtropical high, they are blowing from this high pressure belt, that is your subtropical high, towards the subpolar low, which is a low pressure belt. So they are blowing from southwest to northeast. Same applies in the northern hemisphere. You are now getting to where your polar easterlies are. Okay, I'll just say they are polar easterlies. These one are tropical easterlies. Okay, these are T easterlies. These are polar easterlies. Okay, I'm gonna put it like this. Okay, so in the northern hemisphere you can see the same direction in which they are blowing on our tropical easterlies. You can see it's blowing from northeast towards southwest. Okay, the same applies here in the southern hemisphere. They are blowing from southeast towards the northwest. So this is something that can also be assessed when it comes to your climate and weather, especially on the first 7 marks in section A, 7 marks, and the second one, the match question. You can be assessed on that. Then also generally the direction in which the wind blows. We have got what we call the Coriolis force, and also the pressure gradient. You'll find that the general direction in which the wind blows, especially in both north and south of the equator, is diverted. It is due to what we call the Coriolis force. In the northern hemisphere, it is deflected to the right, and in the southern hemisphere, it is deflected to the left. So you need to know that how the wind direction is also affected just because of the movement of the earth. This is because of our Coriolis force, which means in the northern hemisphere it's deflected to the right, towards the right, and in the southern hemisphere is deflected towards the left. I'm not going to go much into that. So Coriolis force, what it mainly affects is the direction in which the wind is moving. So wind direction is affected by the Coriolis force. That is wind direction. Okay, wind direction, that is your CC, Coriolis force. When it comes now to the wind speed, we are now looking at what we call the pressure gradient. Pressure gradient. Okay, give my spelling. Pressure gradient. This is something to do with the wind speed. Pressure gradient, wind speed. You can see the difference in pressure between two places. That is your pressure gradient. Usually it blows from high to low. So the two, wind direction is affected by Coriolis force. It means in the northern hemisphere the wind is directed towards the right, and in the southern hemisphere it's deflected towards the left. That is your Coriolis force. It affects the wind direction. That is why we end up having it moving from northeast to southwest, from southwest to northeast. This is because of the Coriolis force, which is normally because of the movement of our earth. That is the wind direction and pressure gradient. Basically, we are saying it's more affected by what we call, it all affects what we call the wind speed. When we have got strong winds, we have got gentle wind, we have got light winds, it's because of the pressure gradient, and the pressure differs between two places. This is what results in wind blowing from high to low pressure. Okay, let me rub off, before I rub off this, so now, before I get into mid-latitude cyclones, so mid-latitude, where is this taking place? This is where we have got our subpolar low. So we have got these easterlies that are blowing from the polar, they are cold, which means they're coming from the polar high, they are cold winds that are coming from the polar high. Then we have got the westerlies that are warm, that are coming from the subtropical high. So these two, they meet at the subpolar low. This is more or less of our polar front, where the mid-latitude cyclones takes place in the southern hemisphere, both south and northern hemisphere as well. So we have got these two separated. Our easterlies that are cold coming from the polar high. Then we have got our westerlies that are warm coming from the subtropical high. These two air masses do not meet because they have got different characteristics in terms of their temperature, in terms of the moisture content that they are carrying. So they do not mix, they are separated by a polar front. But however, remember, a mid-latitude cyclone is an area of low pressure. What happens within those, when the two air masses, they do not mix. But however, just because warm air is very light, which means it's undercut by the cold air and is forced to rise. I'll get in detail of how the mid-latitudes form and things like that, okay? But here I'm just giving an introduction so that the moment you understand this as the foundation of your mid-latitude subtropical anticyclones and tropical cyclones, then you won't have any problem. So this is where everything takes place. That is within the subpolar low, where the westerlies that is coming from the subtropical and the easterlies that is coming from the polar high, they do not meet. They are separated by a front. Just because of the difference in terms of their characteristics. This one is cold. This one is warm. And by its nature, the warm is warm and light. What happens? It is undercut by the easterly, then it's forced to rise. Is it rising? I'll get into detail on how a mid-latitude is formed. I just wanted you to have an appreciation of where it is derived from, or where we get our mid-latitude. So this is where it's taking place, our polar front. This one becomes more for polar front. We've got our subpolar low, which is separating the westerlies and the easterlies. So when it comes also to our tropical cyclones, obviously, cyclone, low pressure, warm air is supposed to rise, it cools. Okay, so when it comes now to our tropical cyclone, okay, you can see from here it does not start at 0 degrees because there is no, because of the effect of the Coriolis force. Okay, so what happens? It starts at 5 degrees north, not 50, 5 degrees north and 5 degrees south. This is where it starts. Okay, this is where it starts. In terms of its movement, it's more affected by the easterlies. In terms of movement, it moves going this side. Remember, as it falls to rise, there's latent heat that is produced. It gives more energy to the tropical cyclone. That is why we have having that issue of instability, being unstable weather conditions starting to form. Then from there, what happens is it gets now to 30 degrees north and south. What happens now? It has lost most of its moisture and also it's approaching the land, which means just because of frictional drag. What happens now? Now it has been cooled as it reaches land, then it's been calmed down. But I'll get into detail of that as well. That is part of your tropical cyclone. But I'm just showing you where all this is derived, all coming from the global air circulation. Then from there, we have got our subtropical high. I think this one I've explained in relation to the position of the Kalahari High, the South Atlantic High, and South Indian High, usually, and how it affects the South African weather map. But basically, this is what it's all about in as far as climate and weather is concerned. This is just an introduction. Now I'm going to get into mid-latitudes. After mid-latitudes, I'll also give some explanation on tropical cyclones. Then from there, we move on to subtropical anticyclone. This is just an introduction. I want to try to separate it. So this brings us to the end of our global air circulation. But in form of a summary, let me just sum it up. We are saying that in order for you to understand the mid-latitudes, in order for you to understand the tropical cyclone and the subtropical anticyclone, this should be your foundation. This should be your foundation. Why am I saying that in form of a summary? Be able to identify your pressure belts. This is your equatorial low pressure belt. It is also known as the intertropical convergence zone. It is also known as the doldrum. This is where we've got low pressure. How do we get to that situation whereby we have got low pressure within the equatorial? Okay, the temperatures usually within the equatorial, they are very high. Hence we have got warm air. As warm air is forced to rise, it creates low pressure on the surface. That's why we end up having the equatorial low or the low pressure belt. As that warm air is forced to rise, remember, this is close to the tropics. It is laden with moisture. As it forced to rise, it cools, reaches the condensation level. When it reaches the condensation level, what happens? Clouds of vertical extent, such as cumulonimbus or nimbostratus clouds, are formed. Hence, before it reaches the tropopause in the atmosphere, it diverges in the upper atmosphere. So when you look now at our equatorial low, there's convergence of air masses on the earth's surface and in the upper atmosphere is diverging. When it reaches 30 degrees north and south, now it has lost most of this moisture and the temperature has dropped as well. Remember, it has moved from the tropics, equator, up towards the subtropical. It has lost most of this moisture, hence it's cold, it sinks. And cold air creates clear cloud conditions, there's little or no rainfall. Then from there now, since it's high, it's moving back again. Okay, which means there's convergence on the Earth's surface and divergence in the upper atmosphere. Same applies with here. It's now high, it's moving toward the subtropical low, subpolar low, which is an area of low pressure, which is a low pressure belt. This is a low pressure belt as well. So you've got low pressure belt, high, low pressure, high. This is the distribution in terms of we can see this vertical, there's also horizontal air movement that is taking place there. So all in all, that's what it's all about. In order for you to have a better understanding of mid-latitudes, subtropical anticyclones and tropical cyclones, you need to comprehend or to understand the vertical and horizontal global movements, which in short is our global air circulation. Having our mid-latitudes here, subtropical anticyclones, obviously high pressure, and the tropical cyclones. That's what is very important, I think, for today.